Hey everyone, we're looking at lesson 7 in unit 9. I'm Miss Billman, that's as fancy as my name can get on these papers. So we're going to be looking at the coordinate grid. In this case, it's just quadrant 1 because it's all positive, but I do know that within there in the coordinate plane that we do have 4 quadrants. Again, this is just quadrant 1. Things I also need to take a note of on here when we're looking at these points, and it says they're representing ships at sea. I need to be observant of where these numbers are located because they don't have each line just being 1, right? We actually have to look and see what each line represents. That's one of the first things that I'm going to do. So I see that this is cut into, like quarters. So 0.25, 0.5, 0.75, and 1. And I'm going to go up the X and Y axis, labeling these, which it's going to be easier when we go and the questions ask you what are the coordinates. Now, some people might just hop in here saying each line was 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Well, you would most certainly be wrong then, because we did have 2 numbers labeled on each axis, 1 and 2, and the homework wanted us to be able to figure out what are the correct quadrant, or not quadrants, but what are the correct coordinates. Now, that does require some extra math. I mentioned this in an earlier video, that the cool part about what we're doing and the cool part about math is that we can take these separate ideas and we could put them into one problem. When you took this BA, you really see these in the performance tasks, but it is hidden within all the problems. So here we go. Point A, I go over to the right and I went over 0.75 because I went over 3 spaces, 1, 2, 3. And that'd be my X, and the Y I went up to 1.5. If you were using fractions, you would be at 3/4 and then 1 1/2. You can use either. What I wouldn't suggest is like doing one side in fractions, one side in decimals. That would just be really confusing. So I would stick to 1. That's just me though. Let's look at point B. Point B, they actually have the same X coordinate. So 0.75 or 3/4. But I do not go up 1.5. In this case, I just go up 0.25 or one of the squares, which would be 1/4 or 0.25. Either way, they share an X coordinate. And you can see that even in the fractions where it's 3/4 for both of them, but their distance above is separate. Point C, I go all the way over to 2.25 or 2 1/4, depending on if you're using decimals or fractions. And the Y coordinate is 0.25, which you can see it shares with point B. Point B and point C are on the same horizontal number, and for A and B, they're on the same vertical. So now we need to be able to explain how subtraction can be used to find the number of unit lengths from a ship at point A from the ship at point B, and then write the distance. So things I could do. Some people are going to say, why don't you just count the boxes in between? Great. Love that idea. But not all the time are you given a graph of it. You might just receive the coordinates and they say, hey, what's the distance? So in this case, we're going to be subtracting the Y coordinates. If you look above, when we listed out the coordinates, we have 0.75, comma 1.5 for A, and then 0.75, comma 0.25 for B. If I subtracted the Y coordinates, that would not make any sense at all. So I will subtract the X. It would be 0.75. It just wouldn't make any sense. But if I subtract the Y, it'd be 1.5 minus 0.25, which is 1.25. Or if you're using fractions, they would be 1 1/4 units away. Now, things I could also do. I could count the number of boxes, which is 5, and then I could multiply by 0.25, which would give me 1.25. Either way, I'm getting to the same answer, and I'm using a multitude of different math strategies that I know. So now we need how we can use subtraction to find the unit lengths from point C from the ship at point B. So we're going to subtract the x coordinates. Remember how they're both at 0.25 for their y coordinates? Their x coordinates are different because C is farther to the right. So I would subtract it. And I do 2.25 minus 0.25. If you are using fractions, you're going to be looking at 2 1/4 minus 3/4, and you'll get an answer of 1.5. Again, and I write this in fraction form as well. Whichever you pick, just stick with that, unless the problem somehow says x is going to be fractions, y is going to be decimals. That would just really be a headache, but I would stick with it. The ship at point B is 300 nautical miles south of the ship at point A and 360 nautical miles west of the ship at point C. What number of nautical miles does each unit length? So unit length, we are thinking those grids, that box, the little dashes in between. And I'm labeling this so I can fully understand. I know I can zoom in, and you can do the same thing if we know from A to B how many squares there are. There's 1, 2, 3, 4, 5 squares, and that's 300 nautical miles. From B to C, it's 1, 2, 3, 4, 5, 6, and that's 360 nautical miles. I could then divide, and I could say within those 300 miles, I need to divide it by 5 because there are 5 boxes, so that's 60 nautical miles. So let's check my answer because it should be the same the other way. 360, that's the distance from B to C, or C to B, and I will divide that by 6 because that's how many boxes there were, and I get an answer of 60. So my final answer is 60 nautical miles. When I was looking at doing this problem, I really wrote all over that coordinate plane, which is great. We have that grid for a reason. Use it. It really wouldn't help anyone if we just tried to, recall everything from memory, right? Math is not a game of memory as much as it is looking at strategies and seeing how you apply them. So here we go. Suppose a point, it's at 5 1/2 and then 6 1/2 is reflected across the y-axis. I'm making a coordinate plane and I'm just going to throw that point on there. I know it's positive, so it's going to be in coordinate 1. It's reflected across the y-axis. Boom, I draw an arrow and there we go. It's now in quadrant 1 and then it moves to quadrant 2. So when we do this and it's reflected across the y-axis, the y coordinates of the points are going to stay the same because it's still the same distance up. But the x coordinates will be different because instead of going to the right of 0, we're going to the left of 0. Now, you might be thinking, but Miss Billman, those dots, those are not at 5 1/2 and 6 1/2. You are most certainly correct because I didn't label any numbers. I just know that quadrant is positive. So it's going to start there. And it's going to go to quadrant 2 because it's reflected across the y-axis. So we have the same y, just a different x. The new coordinates for this location are going to be -5 1/2 and then still the same 6 1/2. Just the x-axis changed to being the opposite, which would be negative. For number 6, we're going to be doing something very similar. This is saying, suppose a point is at -7.75 and comma 7.25. And it's reflected across the x-axis. So I just throw a point on there. It does not matter where that location is right now as long as it is in that quadrant. It's reflected across the x-axis. So I draw the arrow down. That is quadrant 3. And I know everything in that quadrant is negative. So yes, the x-axis will stay the same. It's still going to the left. That x-coordinate will stay the same at -7.75. But the y-coordinate will no longer be 7.25 because it will be negative 7.25. This is the beauty of being able to use a model that I did in the yellow to help me think through where these new coordinates would be. Now, my new location is negative 7.75, comma, negative 7.25, and it is super important to attend to precision to make sure you're noting that they're negative. If it moved again across the y-axis, it would move into quadrant 4. Alrighty, thanks for joining me.